Okay, hi everyone. My name is Harald Thommesen and I'm a postdoc here at the Oslo group. And I will now show some results that we got by some preliminary results that we get by analyzing the spider within the Cosmoglobe framework. So now what is SPIDER? SPIDER is a balloon-borne CMB mission that was designed for 2 flights. And the first of these 2 flights was already performed early 2015, where the second one is still in planning phase. And the goal of the mission is to measure B modes on large angular scales at roughly ½ degree resolution. And to better separate the CMB signal from foregrounds, the instrument maps the sky at 2 different frequencies at 95 gigahertz and 150 gigahertz. And the overall goal, when you combine both flights, is to either detect primordial B modes or to constrain them down to R less than 0.03. Okay, now to the instrument. Here you can see the gondola that was carried by a balloon. And here in the middle, you can see the 6 independent telescopes with 3 measured at 95 and 3 at 150 gigahertz. And all these 6 telescopes combined employ 2400 polarization sensitive detectors, which map the sky at ½ degree resolution. And each of these telescopes is equipped with a half-wave plate that's periodically stepped, and that allows to better distinguish the sky signal from any instrumental systematics. And at the upcoming second SPIDER flight, SPIDER 2, some of these detectors will be exchanged for detectors that measure at 280 gigahertz. So that will extend the frequency range of the mission. Okay, so the first flight was launched on 1st of January in 2015 from McMurdo Station in Antarctica. And the flight lasted for 16 days and going on a circular-ish orbit around the pole. And the average altitude of the flight was 36 kilometers. So that's above around 99% of the atmosphere. And that's also the huge advantage of balloon missions, because you can avoid most of the atmosphere while only paying a fraction of actually going to space. So when the mission came to an end, the hardware landed on the ice, and the data disks were almost very soon after recovered, but the instrument itself stayed there for almost another year and was then collected in November 2015, the following summer. And altogether, the instrument collected around 1.6 terabytes of data and mapped about 10% of the sky. And here you can see where SPIDER was looking at on the sky. So this blue field marks the region where SPIDER measured for the science mission. Here's the Southern Galactic Pole. And so that's a region where the polarized dust amplitude is very low. And in addition, it mapped some parts of the Milky Way, but that was for pointing calibration, so not for the actual science mission. Okay, so what's the goal of the SPIDER analysis? So you've seen this plot at least 3 times today, and that actually shows the big picture of Cosmoglobe. So combining several data sets at the time stream level, combining all these steps of the pipeline, calibration, map making, and so on, up to parameter estimation in one code, which then informs the next iteration. And so that's the big picture that we have in mind. But right now, at this stage, we're still running the SPIDER data alone. And we're only concentrating for now on the first step. So we're doing data filtering and map making. So the results that I will show today will be a frequency map of the 150 gigahertz channel for SPIDER when run in the same code base as Quiet and Beyond Planck. Okay, so the goal is to perform an independent analysis of the spider data and to prove that it's computationally feasible to integrate the spider data set into the Cosmoglobe umbrella. And I also want to emphasize that what I'm showing today is in no way related to the results that were published recently. To that, I refer to the talk by Sherry Song on Wednesday. Okay, so now we'll talk a little bit about data preparation. So when you want to load an external data set into Commander, you can't just take your raw data and stick it into Commander. You need to create some unified data structure that is compatible with Commander. So here for Spider, we start out with the raw data, which is about 1.6 terabytes. And yeah, we pick the time streams that we need, and we partition them into 10-minute segments. So each of these segments will contain the data of all detectors, all time streams for the first 10 minutes and the next segment for the second 10 minutes and so on. And then we downsample the data by a factor of 5. So we downsample the data from 120 Hertz down to 24 Hertz. And then we compress the data. The time streams that are compressible, that we compress with Huffman compression. And in our case, that's the pointing and the flags. And finally, we create standardized data files, so HDF files that are compatible with Commander. So we end up with about 2,000 files, which make up about 180 gigabytes. And these data we load into Commander, and the goal is to produce frequency maps for now. So the task at hand is most of the code to do that already exists, but the task is to implement a Commander module that handles all the characteristics that are specific to the data set. And for Spider, these are jumps in the raw data. So this shows a random detector readout for a 10-minute segment. And there are two characteristics. First of all, there are huge spikes, which are caused by telemetry transmissions. And in addition to that, you can see that the offset level, so the level of the signal changes abruptly by many orders of magnitude. So there are huge jumps in the data. And only then when you zoom in to the time stream and you change the range, then you can actually see the sky signal as this sinusoidal dipole, which again, yeah, includes these spikes and slightly smaller jumps. So we can remove these spikes, these telemetry transmission spikes, by simply masking out the time periods where these happen, which leaves us with a gappy time stream. Since we can't work with gappy time streams in Commander, we fill the gaps with constrained realizations, which gives us a continuous time stream that we can work with. And then now we wish to define a data model that best describes these time streams. So we say that the raw data that you see here is the sum of several components. It's the sum of the sky signal, which we are interested in. It's plus an offset term, which traces the changing offset level, a correlated noise term, and a white noise term. So we can rearrange this equation. We can subtract the sky signal, the offset term, the correlated noise term, and which gives us the residual. And we see that if we find good solutions for the sky signal and the noise terms, then the residual should be white. So in the code, in an iterative loop, we sample these contributions such that the residual is white. And yeah, we're starting out with the sky signal. So of course we don't know the sky, but we pretend to know it. So we reobserve a Planck map with the spider beam and the spider pointing, and we subtract that in the first, as the first step, we subtract that from the raw data. The next step is that we have to deal with the offsets, with the changing offset level. And to do that, we need to find out where these jumps happen. So where are these jumps? And we do that by computing a rolling standard deviation along the time stream. And wherever there is a jump, we will see a spike in the time stream. So then we can define a threshold, and wherever the standard deviation exceeds this threshold, these we mark as jump region, which basically splits this segment into 3 smaller segments. Then we can simply compute the offset level. So the average of these 3 segments, we can subtract them. We can align these 3 segments, which gives us something that looks like this. So this looks already a lot better, but we can still see that it's not continuous. So we have another jump here, we have another here. So as I said, we do this in an iteration, and then the next iteration, we do a finer jump search, which happens in exactly the same way, but we simply reduce the threshold, which gives us a finer search. And when we, again, align these segments, we get a residual, which finally looks to be free of discontinuities. So now we move on to the next term, which is the correlated noise term. And as our model, we use a 1/f noise model, which depends on 3 parameters: alpha, the slope, f_, the knee frequency, and σ0, the noise floor. We Fourier transform this residual, we fit the model to it, and then we can compute the correlated noise in a time domain, which looks like this, which we can subtract off of the residual, which finally gives us a white-looking residual. And we do that in our iterative loop until it actually looks white. So to sum up, we start out with the raw data. In an iterative loop, we want to find the offset term and the correlated noise term. Once we have these, we can subtract them off of the data, which gives us the calibrated filtered data. And this we will bin onto the sky. So we simply use a binned map maker. And for each segment, we compute the chi-squared, and then we throw away the bad ones. Okay, and this shows how these sky maps look like. So we've only done an analysis on the 150 gigahertz channel for now. So that's T temperature and Q and U polarization. I can subtract off the dipole, which shows us the CMB. And these maps look very promising. And I can show a difference between Planck. So that's spider temperature minus Planck temperature, which looks very promising. So they agree very well. We see a few point sources. There might be a dipole mismatch, but apart from that, the maps, they agree very well. Okay, so to conclude, we've shown that it's computationally feasible to integrate the spider dataset into the Commander framework, the Commander code base. Some stats, it takes about 8 minutes to read in the data, and it takes about 15 minutes per iteration. And where do we go from this? So the next steps are, of course, to repeat the analysis on the 95 gigahertz channel, because so far we've only looked at the 150 gigahertz channel. And then right now, the solution that I've shown depends heavily on Planck. So I've said that in the first step, we reobserve a Planck map. We subtract it off of the raw data, and that's not a long-term solution. So in the future, of course, we want the the sky to change between our iterations. And that's why we need to add additional data sets to the analysis. So in the near future, we will add Planck in map domain, and in further on the horizon, of course, we want to add further additional data sets at the TOD level, because that's the idea of Cosmoglobe. Okay, we're thankful for the funding we received, and thanks for listening.